Hello everyone, this is the continuation video on solid state. This is solid state part 8. In the previous video, we talked about the two types of planar voids. In this video, we need to discuss non-planar voids. Mainly, there are three types of non-planar voids. One is tetrahedral void, second one is octahedral void, and the third one is cubic void. And particularly in this video, we have to identify uh, where tetrahedral voids are present, how tetrahedral voids are produced, what is the radius ratio, and the location part will be done in the next video. So first, without making any delay, first let us take a tetrahedral void. So basically the topic is non-planar voids. Non-planar voids. So the exact meaning of non-planar void, so the center of the sphere which is forming the lattice and the center of the void are not in the same plane. If they're not in the same plane, then the void is said to be what we call a non-planar void. They're not in the same plane. And we have three types of examples in non-planar voids. In this, the first one is a tetrahedral void. See, first let us take what is tetrahedron, how tetrahedral void is produced, what is the radius ratio. That is our requirement. So, tetrahedron, it has actually four corners. You can see 1, 2, 3, 4. And also there are four triangular faces. So here, this is one triangular face. This is the second triangular face. And this is the third triangular face. And this is the fourth triangular face. And there are four corners and four faces. And the name tetrahedron, tetra indicates a number of faces. It indicates a number of faces, but it's a just coincidence, corners also four. And here, if you see, this is the basic tetrahedron, but during the formation of tetrahedral void, what happened and how this tetrahedral void formed, if you observe, so in solids, the particles are arranged very closely, and you can see these three are the particles of one layer. These three are the particles or atoms or ions, whatever. These three are the particles of one layer, and this is the particle coming from the second layer. But we are taking the structure of the solid, so definitely there will be contact between the particles, and you can see the exact structure of these four particles in the solid will be like this. So this is particle 1, this is particle 2, and this is particle 3. In fact, these three particles belong to the same layer. The three particles 1, 2, 3 belong to the same layer, and there is one more particle. This one belongs to the second layer, next layer. So this one, 1, 2, 3, and 4. If you see, these four particles occupy the corners of the tetrahedron. They occupy the corners of the tetrahedron, and at center, there is an empty space. There is an empty space. That empty space is tetrahedral void. If there is any atom in that tetrahedral void, what is the radius of that atom? The atom which is sitting, the atom which is occupying tetrahedral void, we need to find the radius of that atom, or simply radius of void. And the simple mathematics we are using to calculate the radius ratio. See, for the sake of convenience, so we are taking the diagram like this. So this is atom, sphere which is forming lattice. These three atoms, atom A is coming from one layer, atom B, C, D are coming from second layer. And actually at center there is void, but you don't have this much distance. Only to understand the proof, we have taken the diagram, but in the real situation, the structure is like this. In the real situation, the structure is like this. So what I labeled is, this is A, this is B, this atom is C, this atom is a D, and B, C, D are coming from the same layer, and this is occupying the fourth corner of the tetrahedron, that is atom A we are talking about, and there is one void at the center. At the center of the tetrahedron, there is one void, and that void I am labeling as what we call a E. So you can see this E is present at the center of the tetrahedron, And you know the tetrahedral bond angle. So here this bond angle, you know, that is 109 degrees 28 minutes. And we need to find the radius. We need to find the radius ratio. And from this diagram, you can see, so here A, B are in contact, A, C are in contact, A, D are also in contact. So here A, B, A, C and A, D are in contact. You can see in this picture, you'll be more comfortable here. So here this is A, this is B, there is contact. And this distance we are talking about, and that is 2r, where capital R is the radius of atom which is forming the lattice. And not only this one, this is 2r, this is 2r, this is 2r, this is 2r. In fact, so all edges have the same length, that is 2r. So here this is A, B, A, C, A, D, that is equal to 2r. Not only in this one more point, if you take that is AE, for example, if there is what do we call, if you place void here, this distance we are talking about, and that distance is AE. So that is AE. Not only AE, you can take a CE, BE, DE, anything you can take, that is capital R plus a small r. Capital R is the radius of the particle which is forming the lattice, and the small r is radius of tetrahedral void, right? And here, this is the picture. This is these four A, B, C, D are the atoms forming the lattice. E is tetrahedral void, and this angle is 109 degrees 28 minutes. And I am taking this picture out, that is this triangle out. So that is EAB, whatever it may be, AEB, EAB, whatever it may be. Here I am taking EAB. I'm taking EAB. So this angle, if you take this angle is 109 degrees 28 minutes. That means this total angle is 109 degrees 28 minutes. And I'm taking one more line here like this, that is EF. As a result of this angle becomes exactly half of 109 degrees 28 minutes, which is equal to 54 degrees 44 minutes. 54 degrees 44 minutes. And our intention is very clear, finding radius ratio. And from this diagram, what is AE? If you take AE, that is capital R plus small r. Capital R plus small r. And the distance between A and B, if you take AB is 2r, but if you take exactly the midpoint, so this value, this distance is capital R. This distance is capital R. We have this value, opposite we have, hypotenuse we have. Therefore, we are taking, this is a sine theta I'm taking, and the sine 54 degrees 44 minutes is equal to, so here sine theta is equal to opposite by hypotenuse. So opposite is this triangle I'm talking about, and this is capital R, and this is capital R plus small r, and value sine 54 degrees 44 minutes value is 0.816, and this is R by capital R plus small r. If you take the reciprocal of this, it will be like 1 by 0.816, and this is 1 plus small r by capital R. Our intention is very clear, finding the radius ratio. Send this one opposite side. And you'll be getting the radius ratio, that is 0.225. 0.225. So here, any atom, in order to fit into this tetrahedral void, its radius should be 0.225 times of radius of sphere. In that situation, without any distortion, that atom can comfortably sit in that void. If it is more than that, what will happen in ionic solids? We will discuss, and how to identify these tetrahedral voids. If you take, so here these red color things you can see, black color things you can see, these are belonging to the first layer, these are belonging to the second layer, and you can see these four atoms are in contact. 3 red colored balls and 1 black colored ball. At center there is an empty space, and that empty space is tetrahedral void. So here this is tetrahedral void, tetrahedral void, tetrahedral void, and of course here this is about a tetrahedral void. And most importantly, if you observe, it comes under non-planar void because if you see the center of the void and the center of the sphere which is forming the void are not in the same plane. You can see are not in the same plane. This sphere, if you see, are at the center of this, center of this, center of this. So definitely they are not in the same plane. Hence it is said to be what do we call non-planar void of the first kind. And the second type of non-planar void is octahedral void. The second type is octahedral void. And yes, as usual, first we have to understand exactly what is octahedron and how octahedral void is produced and what is the radius ratio in case of octahedral void. Radius ratio means radius of void by radius of particle which is forming the lattice, right? So this is basic octahedron. You can see here there are 1, 2, 3, 4, 5, 6 corners, and there are 8 triangular faces. So there are 8 triangular faces here. This is the first triangular face, second triangular face, third triangular face, and fourth triangular face. Above the square, there are 4 triangular faces. Below the square, there are 4 triangular faces. Altogether, there are 8 triangular faces. Hence, it is called octahedron. This octahedron, tetrahedron, hexahedron, icosahedron, these names are based on the number of faces, but not based on number of corners. Already told you in tetrahedron, it's just a coincidence. So this is not hexahedron. Hexahedron is a cube. Hexahedron means that has 6 faces. Hexahedron is a cube, but this is octahedron because there are 8 faces. And you can also give one more name for this, that is square bipyramidal, because you can see this is a square, this is a square, and these two are pyramids. One is above the plane, above the square, and another one is below the square. And here, why it is octahedron void means now you can see the atoms. These three are the atoms. These three are the atoms coming from one layer. These 3 atoms are coming from one layer, and remaining 3 atoms you can see here. This is the 4th one, 5th one, and the 6th one. So these 3 atoms and these 3 atoms, altogether 6 atoms are occupying the corners of octahedron. 3 atoms occupy corners, 3 atoms plus 3 atoms, 6 atoms occupy the corners of octahedron. And instead of in this triangle view, you can also see the same picture like square bipyramidal. You can see this is a square. This is a square. 1, 2, 3, 4. These are occupying the corners of the square, and this is above the square and this is below the square. However, it may be visualization. And here this is a square bipyramidal. And at center, you can see there is an empty space, and that empty space is called the octahedral void. This is octahedral void. Octahedral void. So octahedral void is actually formed by 6 spheres or 6 particles. Those 6 particles occupy the corners of what do we call octahedron, and in these 6 particles, 3 are coming from one layer, and remaining 3 are actually coming from next layer. Remaining 3 are coming from next layer, and our intention, we have to find the radius of that octahedral void. And in order to find the radius of that octahedral void, in a simple calculations will take, simple procedure we follow. Ultimately, we need to know the radius. We need to know the radius ratio. So in 2 different ways we can find, but here the simplest way, as I told you now, square bipyramid I'm using here. So here let us take a 1, 2, 3, 1, 2, 4, 5. 1, 2, 4, 5 are occupying the corners of the square. This one, 3 and 6 are like 2 pyramids. Like 2 pyramids. 1, 2, 4, 5 can be taken as a square. 3 and 6 are outside of the square, above and below. Square bipyramidal. Hence it is octahedral is also known as square bipyramidal. And here this void, this ratio we have to find, and undoubtedly there is a contact, no doubt. This is actually lying above like this is the correct picture, but for the sake of calculation we have drawn in a convenient way, but this is the structure. This is the square I have taken. This is the square I have taken, and these are the two pyramids. These are the two pyramids, and here this is the diagram we have taken, but there is a contact. 100% there is contact. So this is actually sitting above like this, and that is opposite side, and here there is contact. And in this, again, our intention is finding a radius ratio. In order to find the radius ratio, in this, let us take this triangle ABC. This is the square of the octahedron. ABC I'm taking, and in this the value of AC is very clear. The value of AC and the value of BC, that is equal to 2R, and also we can say that is a edge length, or that is edge length. So that is A. And here the value of this, if you take the value of this, if you take hypotenuse, if you take, so this is a radius of sphere. Here this is radius of sphere, and at center there is what we call octahedral void. And from this very clear, this is A, and this value will be root 2A according to Pythagoras theorem. And that AB is root 2 times of A. In terms of radius, that is equal to 2 times of capital R plus small r. You can see the picture here to get this result. After getting this, you take either 1 by 2 or 2 by 1. It's up to you, and you will be getting what we call 0.414. 0.414 times of radius of a sphere. So if you want to accommodate any particle in this octahedral void, that particle radius should be 0.414 times of radius of a sphere. In that situation, there is no distortion from the structure. Comfortably, that atom can sit in a what we call void, right? And the last one, cubic void. So in case of cubic void, actually cubic void. So cubic void means obviously this is cube, and a cube has what do we call a six faces. Six faces, hence cube is also known as hexahedron. 8 corners and 6 faces. And 8 corners occupy, 8 spheres occupy the corners of the cube, and at center there is a void. At the body center there is a void. That void is called a cubic void. And how to find the radius ratio of this cubic void? And let us see this diagram here. These 8 are the particles which are forming lattice, and this is cubic void. This is cubic void. And here, if you take this particular distance, that is in fact a body diagonal. The value of body diagonal is root 3 times of A, and in case of simple cube, you already know the particles which are at the corners are touching, and this A is equal to 2R. A is equal to 2R. So here A is equal to 2R, and obviously here root 3A. So this root 3A, you can see this diagram, root 3A. So that is equal to 2 times of capital R plus small r. A is equal to 2R because it is a simple cube. Particles are present at the corners. The one which is sitting at the body center is void. Actually, this is a simple cube. You can see it's a simple cube. At center there is a void. You already know in simple cube, the particles which are present at the corners of one edge are in contact. Therefore, A is equal to 2R, and the body diagonal root 3A is equal to 2 times of capital R plus small r. And if you take the ratio of these two, 2 is 2 by 1 if you take, so A gets cancelled, 2 gets cancelled, and this is capital R plus small r by capital R, and this can be written like this, and send this one opposite side, and you will be getting the radius ratio 0.732. 0.732. The radius of that octahedral, not octahedral, sorry, cubic void is 0.732 times of radius of the particle which is forming the lattice. So this is about voids. In fact, there are 2 types of voids. Voids are broadly classified. So planar voids, non-planar voids. Non-planar voids, the three types of non-planar voids, one is tetrahedral void, second one is octahedral void, and the last one is a cubic void. And this is the end of video number 8, and we'll meet in some other video with some other subtopic. Thank you very much.